Okay, welcome. Before we start with a lecture, with a real lecture, I just wanted to remind you that this Sunday evening, the last chance to register for the exam will pass by. So if you aren't registered yet, I do think everyone who is in here should be registered and probably all in the live stream. But still, I want to mention it, that you have to register for the exam. Second thing I wanted to remind you about, or inform you about, before we start with the real lecture, is that since last week, we know when Daniel Kraus by Flix will give his guest lecture. I already announced that in the first lecture, that he will give a guest lecture at 10th of July. Now we know that the guest lecture will take place on 10th of July, starting at 10:45 a.m. I know that's not a normal time to start a lecture, but that's due to his schedule. Since he is CIO of Flix, he has a pretty tight schedule, so we had to figure out that we start at 10:45. So that's not a printing error. This guest lecture will not be recorded. It will not be live streamed, so it's only for people that are here in place. However, of course, the guest lecture is not part of the exam. That's something to mention also. Maybe I will take one or two examples to create examples in the exam based on Flix, but you do not know about the guest lecture for passing these tasks in the exam. So no worries about that. However, it gives you a good insight on how data science is applied in a real-world company, and that's something that should interest most of you, hopefully. Okay, with these two announcements, we can go to the real lecture. Before we really start with the new chapter of classification, of course, I wanted to ask whether there are any questions regarding frequent patterns we should discuss. If not, we can go to the new chapter, classification. Classification is the next broader method we want to talk about in this lecture. Classification is a method which is pretty similar to the next chapter, which is clustering. Both will have something in common. We will talk about that in the chapter of basic concepts. Then we will talk about three different kinds of methods in classification. We will talk about decision tree induction. We will talk about rule-based classification, and we will talk about bias classification methods. These three methods are all doing classification. However, they are taking different approaches on classification. After that, we will also talk about how to evaluate our results we had with classification or our models, because in classification we train models to classify our results. And we will also talk about a method to combine different approaches or different models together in so-called ensemble methods. And of course, I will close the chapter with a little summary. Let's start with basic concepts. In machine learning, and therefore also in data science, we have two different kinds of learning. We have supervised learning, where we have training data, which is accompanied with labels. So we know about the results these training data sets should lead to. And we train a model to use the data to get to the class, the labels, in our training data. That's what we do in classification. We use a certain data set where we know the class, the resulting class, and we train our model to predict the class of new data where we do not have the labels. So we try to find labels for new data based on the labels we had in the training data. That's supervised learning. In unsupervised learning, we do not have any labels, also no labels in the training data. And we just try to find clusters of data which are similar to each other and therefore suggest that they are of the same class behind that. That's clustering. So the next chapter, that's unsupervised learning. In classification, we can also divide classification into two different subcategories. Most often, classification is about predicting categorical class labels. They are discrete, they're nominal, so we only have a certain amount of class labels we want to predict, and that's the number of class labels we have to think about. For example, we can say we predict gender. Then we have a certain amount of different genders that are available, and these class labels are now the things we want to predict based on different other data sets, attributes. We can also say that we can also predict continuous values. That's, however, most often not named classification, but numerical prediction, where we try to predict a value. For example, if we predict the temperature of tomorrow, that's a numerical prediction, because it can be 23.5 degrees Celsius, can also be 23.5, 5, 6, 7, 8, 9, whatever degrees Celsius. So it's continuous. That's most often not called classification. However, in some literature, you might also see numerical prediction being part of classification. So it's important to mention. Where do we need classification? For example, we can use it in certain financial spheres, where we have the case to predict whether a customer is trustworthy enough to get a credit or loan, where we do have maybe two labels, trustworthy enough or not trustworthy enough. So we can put in their financial data and maybe their credit score and whatsoever, and we simply get a label out of that, approved, not approved for credit. We can have classification in medical diagnosis. For example, a COVID-19 test. This is an example which is 3 or 4 years ago, is somewhat of a classifier. To take a sample out of your mouth, and the test itself predicts whether you have COVID or you haven't COVID. That's a classifier. Of course, not a classifier we will train. That's another classifier we want to train, but that's classifying. We can have fraud detection, we can have web page categorization, we can have an unlimited number of different applications for classification. Classification itself is a two-step process. First, we have to construct and train a model. So we take our test data set, which includes assumed classes for each of the tuples in our test data set, and then we train our model depending on the type of classifier we want to use on this training data set. And it learns somewhat when to predict which class. And after that, we of course have a model usage phase, where we use our model to predict labels on data we do not have yet. Based on this model usage, we can then calculate accuracy from the model. So the better the predictions are of our model on the validation data, I would say, the better the accuracy is. And accuracy is one of the most often used measures to validate a data set, classification model. If the accuracy is acceptable, then we will use the model on even more data sets. So in a small example, we have a training data set in this case, where we do have some academic employees with a name, a rank, and the years they work at the university. And then we have a label we want to predict, whether they are tenured or not. So we have two labels, two classes, two distinct classes, yes and no. This is then fed into a classification algorithm, which we will talk about 3 of them. And then some classification rules are put out of that. They can be easy to read. In this case, we are talking about if-then rule. So we talk about a rule-based classifier in this case. And this rule-based classifier is nice because we can now easily read how the model is working. So if the rank is professor or we are above 6 years, then we are tenured. In every other case, we are not tenured. And then we can use that model on a new data set where we maybe even have labels to calculate the accuracy later, and we have a prediction. And we see that in 3 cases, we predicted the correct class. In 1 case, we didn't. This would lead to an accuracy of 75%, because in 75% of cases, we predicted the correct class, which is not a very high accuracy, I have to admit, in many cases. And if we are fine with the accuracy, we can now use the classifier, the classification rules in this case, to predict unseen data. So, for example, a professor with 4 years of work would be predicted as yes. We do not know whether that's correct or not because it's unseen data. We have to trust our model at that stage. Okay, that's, I think, pretty easy to understand. Now we have to go into the methods. We will start with one of the easier methods, decision tree induction. Decision tree induction is pretty nice because it's also easy to understand. So the classifier we get out of decision tree induction is something we can read as humans. So we can use the decision tree, which comes from decision tree induction, to really understand how these predictions are working. For example, we have a huge data set in here, a huge data set for slides at least, where we have age, income, student status, and credit rating as input attributes. So attributes we use to predict a class. And we have Bayes computer as the class we want to predict. Again, a binary class, so we have 2 possible outcomes, yes and no. If we now train a decision tree induction on that data set, the resulting tree might look like this, where we do have a root node with a decision to make. is our age below 30, below or equal 30, when we go to the leftmost path. If our age is between 31 and 40, then we go to the middle path. If our age is above 40, we go to the rightmost path. In the middle path, we already get a decision. So we know this person will buy a computer. While in the leftmost path and the rightmost path, we have still decisions to be made. But it's easy to read, I think. Everybody should be able to tell me if a person is below 30 and is no student, what is the class we would predict in this case? No, exactly. So pretty easy to read and pretty easy decision to follow. So if you get a decision tree, you can even make the decision, the prediction on new data by yourself. The decision tree induction is the process of this decision tree induction refers to the learning of a decision tree. So we try to find a good enough or as good as possible decision tree for our data set. And the decision tree itself is the figure we have here, where we have a root node, that's the topmost node. We can have internal nodes where we have tests on certain attributes, just like with a root node, but within the tree. We can have leaf nodes, which hold the class labels. They are also called terminal nodes. And we, of course, have branches connecting the nodes together. And they can have decisions, or they can labels with values attached to them. The algorithm to create a decision tree, and that's the next important algorithm. After a priori and fpgrowth, that's also an algorithm you might have to do in the exam. The algorithm works in a top-down or divide and conquer manner, and we have as input a data partition, so a data set, more or less. We have an attribute list, so what attributes can we use, and we have an attribute selection method. We will have 3 different attribute selection methods, which I will explain later on. However, they decide a lot. In the algorithm itself, we first create a new node. So for example, if we start, we create the root node. Now we have to determine which attribute to use for that node. So which decision to be made in the first node or in every other node which comes after. Which is decided by the attribute selection method. So we first have to understand what the attribute selection methods do, but more or less we get an attribute out of that. So for example, the output in this decision tree would have been age of attribute selection method. Then we label the new node with this attribute and the splitting criterion. This is important because we can have, depending on the attribute method, either multi-way splits, so we can have splits for every different value, or we can have binary splits. Just binary splits where we only end up with 2 possible paths. There are attribute selection methods which only allow binary paths. There are methods that allow multi-way splits. If we now have the attribute fully utilized, so every value leading to a different path, then we can remove it from the attribute list because we can never or do not have to use it again. If there are still decisions to be made, that's most often the case if we are ending up in a binary split, then we still leave it in the attribute list. And for each outcome of a splitting criterion, we create a path and we continue with the first step for this path. Seems awkward right now, but it will get easy to understand once we get through an example. There are different stopping criteria in a decision tree induction. One stopping criteria is within our path, within the resulting path, we only have samples that belong to the same class. When this class label belongs, we know that we have to be of this class if we are in this path, so we become a leaf node. If samples in D belong to multiple classes, but we do not have any decisions to be made, then we know that we do not have a perfect classifier, so we do not end up with a certain class, but we only end up with a majority class. So we only have a certain likelihood that we are of a certain class. We still have to create a leaf with that majority class, so the most likely class in this path. And if a leaf, the training data set is empty, then we also have to end up with a majority class. We do have a more detailed algorithm on that in the appendix that might become relevant in the implementation phase for the submission. Just for you as a reference, in the appendix, we will not talk about that, but for the submission, you can take a look at the appendix to have a more detailed algorithm. To be really able to talk about an example of decision tree induction and to really understand that, we first have to talk about attribute selection methods, because only then it works out. An attribute selection method is an heuristic to determine the best splitting criterion we have at hand for a certain point of time. More or less, it's a method to determine the splitting rules. We are more or less getting a ranking for each attribute and therefore then select the best of this ranking. In here, we will discuss the most popular attribute selection methods at the moment, which are information gain, gain ratio, which is based on information gain, and Gini index, which is a totally independent method. There are, of course, a lot more attribute selection methods than these, but these are implemented in most frameworks. Let's start with information gain. Information gain was first introduced in an algorithm called ID3. That's just the extension to that. However, information gain is also part of our algorithms these days. The information gain, and that's the mathematical part right now, we will get into maths right here, is trying to predict the information we need to classify a tuple in our data set. So we want to find partitions with the least impurity. The expected information needed to classify a tuple D is called entropy. So if we are talking about entropy, that's what I'm referring to. So how much information do I need to get to know the class of our tuple? This entropy is defined as info D, so that's the entropy, is defined as minus the sum of the probability that a certain tuple belongs to a class within our dataset. So we go through all the tuples in our dataset and sum the probabilities up how much information we need to predict them. It includes a logarithm in here because information is always encoded in bits in information theory. We have to calculate the information for every attribute in the attribute list. So if we have 3 attributes, age, I'm not sure what the example was, age, student, and credit rating, then we have to calculate the entropy information for every attribute in this attribute list. It's very important that this calculation differs for discrete valued attributes and continuous valued attributes. We can have continuous valued attributes in the attributes we need to predict. Right now we are only talking about classification and not numerical prediction, so the classes are always, fixed. In discrete valued attributes, we know that the attribute has V distinct values. So the expected information to classify a tuple in D based on a partitioning by A is simply we take a look at the different partitions we would create by partitioning the dataset into these partitions, and then for each of the partitions we calculate the entropy we would have at this point. So we take a look, we divide our dataset into different partitions. I have an example later, so I will not draw an example in here. We partition our dataset into the different partitions. Let's do it this way. I will draw a little example. Let's say we have age, okay? And we have the low value. We have, let's say, 2 tuples with low, one tuple with middle, and 1 with high. In this case, we would now take a look at every different combination. So we would take a look at this partition, and this partition. And we would calculate the entropy for this partition. We would calculate the entropy for this partition. And we would calculate the entropy for this partition. And then we would weigh that in a total sum for the new, the total entropy we need if we split our data set. With continuous valued attribute, we of course do not have a finite number of partitions we can create. Because in this case, we have 3 different values, so we have to create 3 partitions. And that's not possible. So we would create possible splits. And now we can reuse age, and now we do not do it distinct, but we do it continuous. Let's say 21, 23, 25, and 27. Doesn't correspond with the low and highs down here. That's just another example. Of course, if we just take a look at these 4 values, they can be assumed also distinct, but we assume these are continuous, okay, right now. Now, if these are continuous, there's no possible way to have V distinct splits by definition. But we can create a binary split in this case. For continuous valued attributes, we would create a binary split. And how can we create a binary split? Well, we can take a look at every possible split A possible split would be, for example, we split at 22 and have one partition up here and one partition down here. That's a possible split. We can have another split at 24, where these values would create a split and these values would create a split. And we can have a split point at 26, where these values would create a split and this value would create a split. And in continuous valued attributes, we do have to calculate the new entropy for every possible split. So we have to calculate 3 different informations in here, or entropies. And every calculation simply calculates the entropy of the one partition and calculates the entropy of the second partition, and then also weighs that with a number of values in each partition. So it's far more labor intensive, because with discrete valued attributes, we only have one calculation to make. With continuous valued attributes, we do have to make a lot of different calculations and, yeah, do the split. These calculations are still not the information gain. The information gain is about how much less information would I need if I would use the attribute as a splitting attribute. And that's simply calculated by, using the entropy we have in the total data set minus the entropy of the partitioned data set. So we simply take a look at the original data set and how much information we would still need, how pure we are in the resulting data set. And of course, we want to have a high gain. So we want to use a lot less information with our split. And that's the attribute we select as a splitting attribute. I know it's confusing right now. It's very dry right now, so we have to take a look at an example. Let's go back to our example we had at the start. In this example at the start, we have, again, 4 attributes: age, income, student, credit rating. And this one label bias computer we want to predict. First, in decision tree induction with information gain, we have to calculate the entropy of the whole data set. So we take a look at the whole data set and calculate its entropy. How can we do that? Well, we take a look at the different classes. If we count through, we see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 yeses and 5 no's. So these 2 classes have to be summed up or subtracted using this formula. So every possible class outcome has to be calculated with the likelihood that it's the outcome. So in this case, it's there's a probability of 9/14 for the class yes, and there's a probability of 5/14 for the class no. Added together and calculated, we end up with an entropy of 0.94. Of course, calculating logarithm dualis in your head is pretty hard. In the exam, we would provide you with idealistic values for logarithm dualis, which are not the real values, but they are easier to calculate values which you are provided with to be able to calculate something like that. But it still might happen. In the exercise, of course, and in the real world, you can, of course, use a calculator. So that's the entropy of the whole data set. Now we have to take a look at every attribute and calculate the partitioned entropy. Let's start with age. Age is in this case is a distinct attribute because we do only have 3 possible distinct outcomes. We have age below 30, below or equal 30, between 31 and 40, and above 40. We can take a look at the classes within these attributes. So if we would split the dataset according to these different values, then we would have 2 yeses and 3 nos as classes within the partition below or equal 30. So let's take a look at that. In the first tuple, we have a no. In the second tuple, we have a no. So 2 no's. Then we have to go down here, a third no, then a first yes, and a second yes. So we have 2 yeses and 3 no's in the partition, only including age below 30. If we calculate the entropy of this partition only, so only tuples that are below 30, or below or equal 30, we would end up with an entropy of 0.97. Calculate that using this formula. So, in the second partition, so 31 to 40, if you take a look only at the tuples including 31 to 40 as age, every attribute outcome is yes. So we only have yeses and no nos. If we calculate the entropy of that, we do not need any further information. Every attribute leads to the class being being yes, sorry. So in this case, the entropy is 0 because we do not need any further information. So that's the best possible entropy we can reach. And then we have an age class above 40, where we have 3 yeses and 2 nos, which again leads to an entropy of 0.971. These entropies can now be used to calculate the information, the entropy of a split. So if we would partition the dataset according to this attribute. If we do that, we have to add up first the entropy for the first class with a likelihood of 5/14, because 5 of the total cases are within that partition. So 5/14 times 0.971 plus 4/14 times 0 plus 5/14 times 0.971, which ends up at 0.694, which is a lower entropy. We need less information after that split than beforehand. So we have an information gain, positive information gain, from as 0.246, because beforehand we would have needed 0.94 as entropy. Afterwards, we only need 0.694 on average. So we have a little information gain if we would use that split. We can calculate that for every other attribute as well. In this case, income would end up at 0.029, student would end up at 0.151, and credit rating would end up at 0.048. Now we know that we do want to use the attribute as our splitting point with the highest information gain. So the attribute where we need less additional information after the split than beforehand. And in this case, age is the best attribute because it has the highest information gain, 0.249. So in this case, we would use age as a splitting point, which would lead to a decision tree like this, where we simply partition our data set according to our splitting criteria. Age below 30, every attribute containing that comes into this tuple, this partition, and this partition. And now we can do the same method for every partition, where we take a look at income, student, credit rating. Why do we do not have age anymore in here? Well, because age is fully exhausted. Age is always below or equal 30 in this case. It's always above 40 in this case. It's always between 31 and 40 in this case. So it's fully exhausted. We can remove it from the attribute list. We can continue that. We do know in this case everything is yes, so we can already create a leave node in here. In the other two cases, we have to continue until they lead to stopping criteria. You will do that by hand in the exercise, so then it should be even more understandable. Of course, you can also try to get to these values with our example data set in here to understand the algorithm further. Are there any questions still here? I know it's a lot, but once you have tried it out, I think it's not that hard to perform. No questions? Okay. Then we can go to the second method of the second attribute selection method. That's the correct way to phrase it. The second method is gain ratio. Gain ratio, as I said, is based on the information gain. It was first used in an algorithm called C4.5. This method is based on the information gain and tries to solve a big problem of the information gain. The information gain has a big problem because it tends to prefer attributes with a large number of distinct values. Let's say, and that's the easiest example to understand that, we have ID. And you should never use ID as a possible attribute in a classification method, or at least in a decision tree induction. But let's say for some reason you forgot it. An ID only has distinct values, of course. And now you have a class, and you have other attributes between that. Let's say you have a binary class again, but well, in this case, of course, if you would partition the data set according to this ID, you would create a singular partition for every attribute. Since the ID is discrete and is unique, you would create a partition for every attribute. And now the new entropy is of course 0 for every case, because you do not need any further information in any case, because 1 always leads to yes. 2 always leads to yes. 3 always leads to no. 4 always leads to no. It's distinct. And of course, ID would have the highest information gain possible, because it would simply remove any necessity for any further information. But that's not a split you want. If you would go to a less significant example, for example, let's say you have an attribute degree program with a lot of distinct values, let's say 287 and 78, sorry, values in this case, and would compare it to a student status with 2 values, of course, the degree program would have a lot less entropy in its partitions than student status. However, you would have a lot more paths in your decision tree. You would suddenly end up with 278 paths to decide from. And it's okay to have a multi-way decision tree, but you do not want to have a too much fanned out decision tree in many cases. So that's something where information gain prefers these extreme multi-way splits. However, in the practice, you most often do not want them. And that problem is tried to solve with information gain. And it's solved by simply normalizing the information gain. So we simply take a look at our, partitioned data set, compare it with the original data set, and use this normalizing factor, the split info, to then take a look at the information gain and divide it through our normalization function. This leads to datasets with a lot of different values being less overpowered, I would say. Since they would be a lot less significant due to a high split info. A big disadvantage is, in this case, if split info gets close to 0, then of course the gain ratio explodes upwards. If we divide through 0.00001, of course we get a really high gain ratio, and that's a big disadvantage, which might lead to problems. Still, since we are not inverting the gain or something like that, we want still to have the highest gain ratio to select for splitting attribute. If we do that on our example, we can of course use the information gain we had for H, which is 0.24 in this case, 26 in this case. And now we only have to calculate our normalization factor, split info, which is done by still taking a look at the different classes. We know that 5 items are within the H below or equal 30 category. We know that 4 of 14 items are in the 31 to 40 category, and 5 are in the above 40 category, which leads to a normalization factor of 1.577. Applied to the gain, we end up with a gain ratio of 0.5. Normalized gain ratio, or normalized gain, called gain ratio, of 0.156, which, if I remember correctly, would still be the highest gain ratio of all these 4 attributes. Since in this example we have a similar number for every attribute. So we have ternary, age, income, and age and income, and binary, student and credit rating. These are not that different, so it's to be expected that the gain ratio do not lead to hugely different results than the information gain, but with bigger difference in numbers of discrete values, of course, it leads to bigger differences. So it's just about, to lower the impact of this, number of distinct values in each group. And to avoid, less high number splits more. Any questions? Okay, then we get to the last method, attribute selection method, which is Gini index. Gini index was first used in the algorithm CARD. It also tries to solve a problem. In this case, the problem is that both information gain and gain ratio are using the logarithm dualis. And calculating the logarithm dualis is pretty expensive computationally. And the Gini index does not use the logarithm dualis and therefore tries to be less computational expensive. Instead of measuring the entropy of a data set, it tries to measure the statistical dispersion of the data set. This is done by first measuring the impurity of a data set. So we also take a look at the whole data set first. So a complete data set. And we now use 1 minus the sum of the probability of all class outcomes to the power of 2. Very important, it has to be a non-zero probability that a class belongs to, that a sample in the class, in the dataset belongs to this class. However, if you only take a look at the possible outcomes, it's always non-zero because there has to be at least one example for this outcome to be present in the dataset, therefore it's non-zero. Then we also have to take a look at discrete valued attributes and continuous valued attributes. In discrete valued attributes, we have this case again, low, low, middle, high, and we have to create partitions. However, Gini index is only working binary. Gini index is not able to do multi-way splits. So this wouldn't be possible. We can't have one partition D1, second partition D2, third partition D3. Rather than that, we have to create all possible outcomes, possible binary splits for that as well, which is done just like with continuous attributes in information gain and gain ratio. And it's done by simply creating one split with the lows in one category and the middle and high in another category. The lows in here and the middle and high in one group, which is one combination that is possible. And our possible combination would be low and middle in a group, but high in another group. And then we can, of course, have low and high combined and middle in a singular group. So we have, again, 3 possible combinations we can have. which makes a lot of possible combinations we have to go through. For continuous value attributes, we can still use this splitting because it leads to binary splits. In both cases, we have to take a look at the probability for the partition times the measured impurity, so this formula of the partition or within the partition, plus the probability for the second partition times the measured impurity in the second partition, which is pretty similar to information gain and gain ratio, but now without logarithm. And now we try to find the highest reduction of impurity, which is simply the original impurity minus the impurity after the binary split. And we select, of course, the attribute with the highest reduction of impurity as the splitting attribute. Example, in our original data set, we have to calculate the measured impurity of the whole data set, which is 1 minus the probability of yes, so 9/14 to the power of 2, minus the probability of no, which is 5/14 to the power of 2, which ends up at 0.459. Now we have to take a look at the different classes. Here we start with income. Income has 3 different values, high, medium, and low. So we have to take a look at 3 possible subset combinations. One possible subset combination is putting low and medium into one partition and high in another partition. In that case, for low and medium, these would be 10 of the 14 cases because 4 are high. We have a Gini index, measured impurity of 1 minus 7/10 minus 3/10. So we have 7 yes, 3 no within the 10 low or medium groups. And we have two yeses and 2 nos in the other cases, which would lead to a reduction of impurity, not reduction of impurity, but measured impurity of 0.443 in the split. So we have a reduction of impurity of only 0.016. However, if you take a look at the other subsets, so the combination where medium is dataset 2 for itself, and low is alone, and the other 2 build the other partitions, of course. I didn't write that down in here. That's not official notation, but you can write it down in here. We see that still this partitioning would lead to the highest reduction of impurity. So the other 2 splits have a lower reduction of impurity. So for income, this is the best split. That's calculated by comparing every reduction of impurity within income. So the representation for income would become low and medium in one group and high in the other group. And then we have to calculate the Gini index, of course, for all other attributes and choose the attribute with the highest reduction of impurity. I know that's somewhat confusing, but hopefully everybody understood. Or are there any questions? How to get to these values, especially? Are there any questions? Or is everybody understanding how we get to these values? There are 2 possible outcomes for me right now. One is everybody understood, which is not that likely, or everybody is so far behind that they do not want to ask any question, but there are no stupid questions, so ask if you need to ask a question. Okay, yeah, then yeah, there is an exercise on that, so hopefully with the exercise on that, it becomes easier to understand. Yeah, that's the 3 attribute selection methods. We do that and then use the decision tree induction algorithm as a wrapper to go through the whole data set and end up with a decision tree. The 3 methods are very often used, but they have disadvantages for themselves. Information gain, it's pretty obvious. We have these bias towards multivariate attributes. So the more values an attribute has, the more likely it is selected as a split point, which is solved by gain ratio. However, it tends to overcompensate for this. And when we have Gini index, it's also biased to multivariate attributes. However, it's less significant because we only have binary splits, and therefore that's not a big problem. However, it has a lot of difficulty when the number of classes is very large, since we have a lot of calculations to make them. And it has a tendency to favor equal size partitions and purity in both partitions. That's something that might become a problem in some certain domains, but is okay in most cases. And a big advantage of Gini index is, of course, we do not have logarithm dualis to calculate. However, we therefore have to calculate a lot of different combinations in a singular attribute. Yeah, with decision tree induction as a whole, we also have a big problem with so-called overfitting or classification. We have a problem with overfitting. But especially with decision tree induction, we have the problem that if we have a small training data set where 1 or 2 anomalies or noise or outliers are included, which is pretty normal that these are included. Of course, we try to see that in the data reprocessing, but let's say we didn't see it. Then there's a high likelihood that we get a branch only representing that singular outlier anomaly. If that outlier occurs in our training data set, but very rarely occurs in the real world, of course, these anomalies would lead to poor accuracy in unseen samples or new samples. And that's called overfitting. We overfitted our model to the training data. And that's something we want to avoid. It can be avoided by taking a look at branches after the decision tree induction, which occur very rarely. So for example, only 1 case leads to that partition in the whole data set. Then we would prune that branch because it's too rare to be of any significance. There are 2 cases of pruning where we either introduce a certain stopping criteria, so an excess stopping criteria where we say, hey, if we are in a partition that only includes 1 or 2 tuples, also stop and do not go further. Or post-pruning, so we do the whole decision tree induction and then we remove the branches afterwards. But that's something that you should most often do. Of course, there's a lot of research in decision tree induction to enhance decision tree induction. For example, there are new methods which allow for continuous valid attributes. We already talked about how to handle continuous valid attributes with something like this, but there are new methods which try to avoid these multi-way splits, only allowing binary splits, and try to find ways to do multi-way splits. Then we, of course, have a problem with missing attribute values, which can be solved by some preprocessing as well, where we simply introduce common values for the attribute. We can also use classification to fill out these missing attribute values, of course. We can predict how likely a certain value is if it's missing by using the other attribute values. And of course, we can construct new attributes, but that's something we already mentioned in preprocessing. There's a big problem with decision tree induction because all these methods are not very scalable. So ID3 for information gain, C4.5 for gain ratio, and CART for gene index. They always need the whole dataset to be in memory. Of course, for real-world dataset, Amazon scale, that's not very likely. We can try to extend the basic algorithms to handle these large datasets. In KDD, we will take a look at two small examples and how we can start doing that. However, we won't get into much detail on that. We will have rainforest and we will have boat. In rainforest, we try to take a look at the original dataset and first extract all the data we need for our attribute selection methods, so information gain, gain ratio, and whatsoever, gene index, and try to store it in a very compact data structure. And then we simply use the original data algorithm to not use the original data, but the compressed data structure. That's done with a so-called AVC list, an attribute value class label list. And an AVC set is linked to a certain attribute, which is the aggregated projection of the dataset onto that attribute, and an AVC group, which contains all sets. Let's take a look at the original dataset and its AVC set. The AVC set on age would simply include, hey, in age below or equal 30, we have 2 yeses and 3 no's. And 31 to 40, 4 yes and 0 no's. Above 40, 3 yes, 2 no's. That's all we need to calculate the information gain. We can do the same for income, we can do the same for for student, and we can do the same for credit rating, of course. And therefore, we do have all the information we need for the first split, which is very nice because it's far more compressed. This is far less than this. And we can still use our original algorithms. However, of course, it's still limited. If a dataset has too many different values with too high counts, it still might get to a limit. In boat, we scale in a different way. Boat is about bootstrapping. And the full name for boat is Bootstrapped Optimistic Algorithm for Tree Reconstruction. So that's the full name in here. And the basic idea of bootstrapping is simply to use samples. We do not use the whole data set, but we use samples. And we use more or less a statistical technique to get to good samples of the original data set. So we have some subsets of original data sets. These samples fit into our memory and can then be used to induce a decision tree. And after taking a look at different subsets and training different decision trees on these subsets, we combine the trees together into one big tree. This has been, in the past, this has been evaluated, and it has been shown that the resulting tree of training multiple trees on subsets, combining them together, often leads to a very similar tree to the full trained tree. This only needs 2 scans on the database, since we only have to go through the database once for creating subsamples and then to creating the thing. We can do that also in incremental steps, where we take insertions and deletions of training data for updating the decision tree, because we already have an algorithm to combine different trees together. Bootstrapping will also become relevant in the ensemble methods part of our lecture, so probably next week. Bootstrapping is, and that's the process of having multiple samples, training multiple models, and combining them together. Yeah, that's decision tree induction. The next chapter, rule-based classification, is pretty similar, has a lot of similarities to decision tree induction. And that's the reason why I will start talking about rule-based classification, and hopefully I will also be able to get through. Rule-based classification is simply based on a set of if-then rules. You might remember the first example of classification we did today. We had this: if age is below 30 and we are professor or whatever, then we are of class tenured. This is simply an if-then rule. An if-then rule consists always of 2 parts. The if, so the antecedent, the precondition, so which conditions have to be satisfied, and then the consequent, what happens if these preconditions are fulfilled. Most often, the then is simply which class we are in. And the if is the other part. For example, one rule might be if age below 30 and student yes, then buys computers yes. They are very easy to read. I would even argue easier to read than a decision tree. And we can really understand them. If we have a set of rules, we can use them to classify new tuples. For example, if you have that set of rules, very easy to read, can you tell me what the class of the first tuple is? Raise your hand if you are of opinion the new class is yes. If you are of opinion of class no. Okay, all are of opinion that it's yes. Yeah, it is, because the first rule already targets that we are in a price below 1,500, and therefore we are of class yes. In the second rule, we have a problem. Why do we have a problem? Because more than one rule is triggered. Namely, the second rule and the third rule. since we are in a price above 1,500, the color is red. This rule would apply, but also the location is Erlangen, so we are both by no and by yes at the same time. That's the problem with rule-based classification. And this leads to conflicts. It might also happen that we do not have any rule that is triggered. How can we do that? How can we solve that? We can solve that in two cases, ways. First, let's talk about more than one rule is triggered. This can be, for example, solved by having a priority queue. So we have priority attached to each rule, and we assign the class of the highest priority. We can also have a class-based ordering. So of the conclusion, we take a look at how expensive it is to be in a class, for example. Let's go back to COVID-19 tests. It's maybe better to predict that you are probably having COVID than telling you, no, you do not have COVID, and you going out and infecting other people. So it would be better to predict a yes than a no if you have a conflict to avoid infections. And we can have class-based ordering. Of course, we can have also rule-based ordering, which is more or less size ordering. For no rule is triggered, we should simply introduce a default fallback rule. So what happens if no rule is triggered? What's the default class? That's simple to solve. Rules, if-then rules, can easily be extracted from decision trees. So we can use decision tree induction to create if-then rules. Why should we do that? Because rules are far easier to understand than large trees. So if you have a very big tree, it's easy to have if-then rules for that. And basically the idea is simply to take a look at each path from root to leaf and creating an if out of that, and then using the leaf as a then. So if we take a look at our original tree, then we can simply use the leftmost path, age below or equal 30, student yes, to create a new rule. We can do the same for the second leftmost path, age down here, down here, down here. This is the second rule. We can create a lot of rules out of that. It's simple to do. A rule has to fit the tree to be matching. So if age below or equal 30, then yes would not be fitting this tree, so can't be extracted from that tree, of course. However, of course, extracting rules from a decision tree is not the only way to learn rules. There are other methods. For example, the sequential covering method. In this case, as the name suggests, rules are learned sequentially. We try to cover as many tuples of a given class as possible while having as least as possible tuples of other classes being covered. That's something we can easily show with a visual example. Let's say we have a two-dimensional sphere and we have two classes. Now we want to use a sequential covering algorithm for that. We try to find a rectangle let's say we only have rectangles, we can of course only have circles and whatever, but in this case we only have rectangles, okay? And we now try to find a rectangle that covers as many tuples of a given class as possible. We start, of course, with an empty set of rules, and then we find the first rule which covers the most tuples of one class without covering too many of the other class, which might be, for example, this rectangle. Then we remove these tuples covered, and we do the same. And we do that until either no more rules are left, or the quality of a rule is below a certain threshold. The quality of a rule simply talks about how many real tuples are covered and how many other tuples are covered. There are a lot of sequential covering algorithms, for example, FOIL, AQ, CN2, and Ripper. The FOIL is more or less based on information gain, where we do have, FOIL stands for First Order Interactive Learner, and we do have two rules. One rule is if condition then class C, and the other is if condition, other condition then class C. Then we take a look at how many positives and negatives, so how many of the real of class C are covered, and how many of class other than C are covered, and we do that for both rules, and then we try to assess the information gained by these two conditions, and if we find a rule with a high FOIL gain, of course we use that rule. FOIL favors rules with a high accuracy, so we try to find, again, rules having a lot of own classes and less of the other classes, which is basically the same. Yeah.
Is both C's the same class?
Both C's are the same class, yes. We are taking a look at only class C in this case. So we only take a look at, for example, class yes. And we try to find a good covering method for class yes. And we try to compare the two rules simply against each other. So we compare one rule with a set of conditions and another rule with our conditions, and then we select the rule with better accuracy, and we continue that until we find the best rule possible. Okay, that's a very quick run through of rule-based classification. Bias classification methods are bigger, and I would argue they are even more complicated than decision tree induction methods. So we will do that next week. Do you have any questions regarding these first two major chapters within classification? Doesn't seem like it. Then I also want to point out the first submission is running currently. So if you want to get access to the mock exam, which is really recommended, maybe start working on the submissions. It's about a priori and FP growth. It will teach you a lot about your strengths and weaknesses within a priori and FP growth. Even if you're not good with Python yet, I would really recommend you to work on that. First, since you would need Python in your later life, maybe, especially if you're a data scientist or want to become a data scientist, but also in other domains, it's helpful to know a little bit of Python. Secondly, you are allowed to work in groups, so You can always try to find one with some more experience in Python, and you can learn from them. But really do the submissions. And yeah, then I do not think that I have more to say, so I leave it at that and see you next week. Have a nice time.